Hey everyone. Okay, well, we figured out how we can find exoplanets, right? The two main ways to detect exoplanets are with the Doppler method and the transit method. And now that we've got that, what else can we do? What else can we figure out? What other properties of a planet can we figure out from the measurements that we kept, well, the properties that we've been able to determine so far? Well, we'd like to know, what's the planet made of? What is the composition of these planets? And you can get a handle on what the planet is made of by looking at its density. This graph here is a plot of the mass of the planet versus its radius for the first couple of hundred exoplanets that were ever discovered. And shouldn't be a wild surprise that if the planet is more massive, it also tends to be larger. But it also tells us something about what the planet is composed of. Because each of these blue curves is what the mass and radius relationship would be if the planet were purely made of iron, rock, water, and hydrogen gas. So by looking at where these planets lie on this graph, we can get a handle on what they're made of, right? The blue triangles are the planets in our solar system. So there's Mars and Earth, Uranus and Neptune, Saturn and Jupiter. And it shouldn't be a wild surprise, right? What are the terrestrial planets made out of? What are Mars and Earth and Venus made out of? Well, they lie right between the lines for rock and iron. And what are the terrestrial planets made out of? They're made out of a mixture of rock and metal. Not pure iron. When we talk about metal in our planet, it's iron and nickel and some other kinds of metals, but still, it is a mixture of rock and metal. Uranus and Neptune, the ice giants, are in between the curves for water and hydrogen. So what are the ice giants made out of? Well, they're made out of mostly a mixture of water and hydrogen, but they're closer to the line for water. They're closer to the line for ice. So they're made out of more ice, less gas, which is why we call them ice giants. Saturn and Jupiter are in between the curves for gas and ice. So they're made out of mostly a mixture of gas and ice, but they're closer to the curve for gas. So they're made more of gas and less of ice, which is why we call them gas giants. And so if we wanted to just find a new planet, figure out its mass by using the Doppler method, figure out its radius by using the transit method, and then plot that planet on this graph, we would get a good handle on what it's made out of. Is it made out of a mixture of gas and water, or water and rock, or rock and iron? That would give us a good first step. If we really wanted to know what the planet was made of, though, let's calculate its density. And what is density, right? When we're talking about the density of an object, we're talking about how much mass that object has per unit of volume, right? How many kilograms is it per cubic meter? Or, for our purposes here, how many grams of mass is that per cubic centimeter? How could we figure that out for planets? Well, the mass we can get from the Doppler method. The volume, how can we figure that out? Well, the volume for a sphere, right? Every planet is spherical in shape. And the formula for the volume of a sphere is its 4/3 pi times the radius cubed. So we figure out the radius of the planet using the transit method, plug that in here, we'll get the volume of the planet. Mass divided by volume gives us the average density of the whole planet. How do we want to measure that? Well, so far we've been and the formulas that we use for getting the mass and the radius, we've been finding the mass of an exoplanet in Earth masses. We've been finding the radius of the planet in Earth radii. And here we're going to have to do a little bit of converting, because our life is going to be a whole lot easier if we find the density of the planet in grams per cubic centimeter. Because if you have a planet that is made of pure gas, pure, mostly hydrogen gas, it'll have a density of 0.5 grams per cubic centimeter. A planet with a density, or a planet made of pure water will have a density of 1 gram per cubic centimeter. If the planet is pure rock, it'll have a density of 3 grams per cubic centimeter. And if it's pure metal, 8 grams per cubic centimeter. So, to get the average density, we're going to need to do some unit conversions. Because to find the average density of the planet, we need the total mass divided by the total volume. So we got the mass of the planet, and as we said, we probably have the mass of the planet in Earth masses. We're going to need to convert that into grams. We've got the planet radius in Earth radii. We're going to need to convert that into centimeters, which is a little bit annoying, but what that means is that if we have the mass in grams and the radius in centimeters, then we'll calculate the density of the planet in grams per cubic centimeter. And then we can compare that number to these numbers to get a handle on, so what kind of materials is this planet made out of. So that'll be a 4-step process. Converting the mass into grams, the radius into centimeters, calculating the volume in cubic centimeters, and then dividing the mass by the volume to get the density in grams per cubic centimeter. Looks a little bit annoying. Looks like a little bit of work, which means it's a perfect situation to have our spreadsheet do this for us. So, step 1. I'm going to make this a little smaller. Make this a little smaller and say, all right, step 1, converting the mass into grams, where 1 Earth mass is 5.97 times 10 to the 27 grams. So how would we convert that? Well, if we're wanting to convert from the number of Earth masses, so I'll put my mass in Earth masses right there. I multiply by 5.97 E27 grams per Earth mass, and that gives me the total number of grams. Then I want to convert the radius into centimeters. And 1 Earth radius is 6.37 times 10 to the 8 centimeters. So 6.37 times 10 to the 8 centimeters. So then here I'll tell my spreadsheet, okay, grab the number of Earth radii in the radius of the planet times 6.37 E8 centimeters per Earth radius, and that'll give me the number of centimeters in the radius of that planet. Okay. Move that there. Okay. So let's calculate the volume, right? The volume is going to equal 4/3 times pi. Remember, if you put pi and then open close parentheses, that'll tell the program to go take the value of pi and plug it in right there. 4/3 times pi times the radius in centimeters cubed. Okay, that'll calculate the volume in cubic centimeters. And then the density is just mass divided by volume. Okay, so if I have a planet like Earth that has 1 Earth mass and 1 Earth radius, then the average density of Earth is 5.51. Well, what does that mean? Well, if your planet has if your planet has a density between 3 and 8, then if the planet has a density of 3, then it's pretty much 100% rock. If it has a density of 8, it's 100% metal. If it has a density like 5.5 that's in between 3 and 8, then the Earth must be made out of, no surprise to us, mostly a mixture of rock and metal. If the planet has a density between 1 and 3, then it's got a density between ice and rock, which means the planet is mostly made of ice and rock. And that describes an ice giant. And if the planet has a density less than 1, essentially that, a density between 0.5 and 1, or any number less than 1, will mean that the planet is mostly made out of ice and gas, which describes a gas giant. So this one number, the density, because we put in the work to convert our values so that we're getting the density in grams per cubic centimeter, then we just need to eyeball that number and go, oh, less than 1, gas giant. Between 1 and 3, ice giant. More than 3, terrestrial. Problem solved. Now, I said a second ago, right? The Earth's density is 5.5, so the Earth is made of a mixture of rock and metal. Well, is the Earth purely rock and metal? Is there no water on Earth? No, of course there is. Is there gas on Earth? Yeah, of course there is. We're breathing it right now. So every planet is going to be made out of a combination of all 4 components. But what's the majority? Right? If the density of Earth is in between the density of rock and metal, then the Earth is mostly made out of rock and metal, and the water on Earth and the atmosphere of Earth is not enough to really change the density substantially. So if you're trying to model what a planet is made out of, and you'll see questions like this in the Taurus homework, you've got a planet, it's going to give you the mass and the radius of this planet, in this case Saturn. Okay? It gives you the mass and the radius. You're going to calculate the density, and since we've already got our spreadsheet to do the math for us, then all you need to do is enter your mass and radius into the spreadsheet. It'll calculate the density for you. Use that density to figure out what the 2 major components are. And here's where this makes life a lot simpler. If the density is less than 1, then it's mostly gas and water. So you can make that planet out of just gas and ice. If the density is between 1 and 3, then it's mostly made out of ice and rock. So you can make the planet out of just ice and rock. If the density is between 3 and 8, then the planet's mostly made out of rock and metal. That's all you need to make the planet out of. If you're trying to model what a planet is made out of by playing around with all 4 components, you're making a much harder job for yourself. Simplify it. Figure out which 2 materials. If it's a terrestrial, it's made out of rock and metal. If it's an ice giant, it's made out of mostly ice and rock. If it's a gas giant, it's made out of gas and ice, and you can ignore the other 2. Just figure out what the 2 materials are that overwhelmingly compose the planet, and you can figure out what percent is gas. If it's a gas giant, you can figure out what percent is gas, what percent is ice, and you can leave those other 2 at 0, not because there's absolutely no rock and metal inside of Saturn. There's just so little that it doesn't really affect the density that much. So when you're doing these problems, you're going to when you're solving these problems to model what the planet is made out of, just pick the main 2 components, ignore the other 2. It's going to make your life a lot easier. Okay? The density is the key indicator for what type of planet you're talking about. If all we had was the mass or the radius individually, if all we had was just the mass or just the radius, then we could try to guess about what type of planet you're talking about. But the density is the way to know for sure. Calculate the density, figure out what the 2 main components are, and then you know for sure, that's a terrestrial like Earth or Venus or Mars or Mercury, Or is it an ice giant like Uranus or Neptune? Or is it a gas giant like Jupiter or Saturn? Okay. So now we're off to the races, trying to figure out, based on the things that we can determine from the planet, like mass and radius, what else can we figure out? And what the planet's made out of, its composition, is a really powerful tool for figuring out what the planet's like, what it's made out of. All right. So go ahead, work on some more problems to practice that, and have a good day.